Article 110.26 does not specifically apply to transformers. However, the working space requirements of Article 110.33 apply to all equipment, including transformers. A 480 volts panel board across the aisle from a 480 volts to 208 volts transformer would require 4 feet between them per section 110.33. The working space requirements of Article 110.33 apply to the front and back of the transformer, but not to the sides. The amount of space required on the sides for running conduit and pulling wire is typically determined by the manufacturer's installation instructions or by industry best practices. Transformers are typically fed with a load break elbow into the side. The load break elbow may require a minimum space of 18 inches on the side for access. Transformers do not typically require breathing room behind them. However, it is recommended to leave some space, typically 6 to 12 inches, behind the transformer for maintenance and ventilation. Regarding working space, it's crucial to differentiate between the requirements for general electrical equipment and those specific to transformers. While Article 110.26 addresses working space around electrical equipment operating at 600 volts, nominal or less, to ground, Article 110.33 is applicable for installations over 600 volts, nominal. Since the response mentions a 480 volts panel board and a 480 volts to 208 volts transformer, it appears we're dealing with equipment that falls under the scope of Article 110.26 as well, though the answer specifically references 110.33. Let's delve into the details for clarity. Article 110.26 outlines specific dimensions for working space in the direction of access to live parts operating at 600 volts or less. These dimensions vary based on voltage to ground and condition. Condition 1 involves exposed live parts on one side and grounded parts on the other side, or exposed live parts on one side and insulated parts on the other side. Condition 2 involves exposed live parts on both sides of the working space, but the operator is guarded. Condition 3 involves exposed live parts on both sides of the working space and the operator is not guarded. It is important to consult the specific table within Article 110.26 to determine the required depth of the working space based on the specific voltage and condition. Now, regarding the 4 feet requirement between the 480 volts panel board and the 480 volts to 208 volts transformer, this dimension likely stems from a misinterpretation or a conflation of requirements. If both pieces of equipment are operating at 600 volts or less, the working space requirements of Article 110.26 would apply. However, the specific distance would depend on the conditions present. For example, if there are exposed live parts on both the panel board and the transformer, and the operator is unguarded, then Condition 3 would apply, and the required working space might be greater than 4 feet depending on the voltage. In terms of the sides of the transformer, the general rule is that working space is primarily required in the direction of access for examination, adjustment, servicing, and maintenance of the equipment. Therefore, while Article 110.26 dictates specific working space in front of the equipment, it doesn't explicitly define requirements for the sides or rear, unless access to live parts is required from those locations. However, it's crucial to consider the manufacturer's recommendations and industry best practices for providing adequate space for conduit entry, cable termination, ventilation, and general maintenance. The use of a load break elbow for connecting to the side of the transformer is a common practice, particularly for pad-mounted transformers. The 18 inches clearance recommendation is reasonable, as it allows sufficient room for manipulating the elbow during installation and maintenance. As for the transformer's proximity to a wall, it's generally acceptable to position the transformer close to the wall, but leaving some space for ventilation and maintenance is advisable. The specific distance will depend on the size of the transformer, its cooling requirements, and the type of maintenance that may be required. A clearance of 6 to 12 inches is a good rule of thumb. In laying out an electrical room, several other factors should be considered in addition to working space. These include adequate lighting, proper ventilation, sufficient headroom, and clear access pathways. It's also essential to comply with all applicable codes and standards, including the National Electrical Code, as well as any local or state regulations. In summary, while the response provides some useful information regarding transformer working space requirements, it's crucial to consult the specific sections of the National Electrical Code in the manufacturer's recommendations for accurate and complete guidance. Remember to carefully assess the specific conditions present in the installation to determine the appropriate working space and clearances. When dealing with electrical installations, consulting with a qualified and licensed electrician is always recommended to ensure safety and compliance with all applicable regulations. Let's delve deeper into the considerations for transformer installation, focusing on best practices and code compliance beyond the basic working space requirements. Firstly, consider the environmental conditions where the transformer will be located. Transformers generate heat during operation, so adequate ventilation is crucial to prevent overheating and ensure optimal performance. This is especially important in enclosed spaces like electrical rooms. The ventilation system should be designed to remove the heat generated by the transformer and maintain a safe operating temperature. The amount of ventilation required will depend on the size and type of transformer, as well as the ambient temperature of the environment. Secondly, think about the structural support for the transformer. Transformers can be quite heavy, so it's important to ensure that the floor or mounting structure is capable of supporting the transformer's weight. Consult the manufacturer's specifications for the transformer's weight and dimensions, and ensure that the supporting structure is designed accordingly. If the transformer is to be mounted on a wall, make sure the wall is strong enough to support the transformer's weight and that the mounting hardware is properly installed. Thirdly, factor in the accessibility for maintenance and repairs. Transformers typically require periodic maintenance, such as cleaning, inspection, and testing. It's important to provide adequate access to the transformer for these activities. This includes sufficient working space around the transformer, as well as clear pathways for moving equipment and personnel. Consider the location of doors, windows, and other obstructions that may impede access to the transformer. Fourthly, address the safety considerations. Transformers operate at high voltages and can pose a significant electrical hazard if not properly installed and maintained. Implement appropriate safety measures to protect personnel and equipment. This includes providing adequate grounding, installing protective devices such as fuses and circuit breakers, and posting warning signs to alert personnel of potential hazards. It's also important to ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the specific requirements for transformer installations. Fifthly, account for noise considerations. Transformers can generate noise during operation, which can be a nuisance in some environments. Consider the location of the transformer relative to occupied spaces, and take steps to mitigate noise levels if necessary. This may include using sound-absorbing materials, isolating the transformer from the building structure, or installing noise barriers. Sixthly, plan for future expansion. As your electrical needs grow, you may need to add additional transformers or upgrade existing ones. Consider the potential for future expansion when designing the electrical room. Provide adequate space for additional equipment, and ensure that the electrical system is designed to accommodate future loads. Seventhly, consider the type of transformer. There are different types of transformers, such as dry-type transformers and liquid-filled transformers. Each type has its own unique installation requirements. Dry-type transformers are typically used indoors and do not require special fire protection measures. Liquid-filled transformers, on the other hand, are typically used outdoors and require special fire protection measures such as containment barriers and fire suppression systems. Eighthly, coordinate with other trades. Installing a transformer typically involves coordinating with other trades, such as mechanical, plumbing, and fire protection. Ensure that all trades are aware of the transformer's location and requirements, and that their work does not interfere with the transformer's operation or maintenance. Ninthly, document the installation. Keep a detailed record of the transformer installation, including drawings, specifications, and test reports. This documentation will be useful for future maintenance and repairs, as well as for troubleshooting any problems that may arise. 10thly, stay up to date with code requirements. Electrical codes and standards are constantly evolving, so it's important to stay up to date with the latest requirements. Consult the National Electrical Code and any local or state regulations to ensure that the transformer installation complies with all applicable codes. Remember to always prioritize safety when working with electrical equipment, and consult with qualified professionals when needed. The safe and reliable operation of your electrical system depends on it. Now let's refine our understanding of transformer clearances and working spaces, specifically focusing on the application of the National Electrical Code, NEC, and industry best practices. Firstly, NEC Article 110.26 addresses working space about electrical equipment operating at 600 volts, nominal, or less to ground. This section mandates sufficient access and working space for safe operation and maintenance. The depth of this working space, as previously discussed, depends on the voltage and the presence of grounded or live parts on opposing sides of the equipment. It's crucial to consult the relevant table within Article 110.26 to determine the exact dimensions required. Secondly, while Article 110.26 primarily focuses on the front of the equipment, it doesn't explicitly dictate clearances for the side or rear, unless access to live parts is required from those locations. However, practical considerations necessitate adequate space for conduit entry, cable termination, ventilation, and routine maintenance tasks. Industry best practices typically recommend maintaining a minimum clearance of 3 feet on all sides of the transformer to facilitate these activities. Thirdly, for transformers operating at voltages above 600 volts, nominal, NEC Article 110.34 governs the working space requirements. This section stipulates larger clearances than Article 110.26, reflecting the increased hazards associated with higher voltages. The specific clearances depend on the voltage level and the configuration of the installation. Fourthly, the manufacturer's installation instructions often provide valuable guidance on required clearances and working spaces. These instructions may specify minimum distances for ventilation, cable bending radii, and other factors that can affect the transformer's performance and longevity. Always consult the manufacturer's documentation before installing a transformer. Fifthly, accessibility is a key consideration when determining transformer clearances. The working space should be readily accessible and free from obstructions that could impede access for maintenance and repair. This may involve providing dedicated access pathways, installing ladders or platforms, and ensuring adequate lighting. Sixthly, ventilation is another critical factor. Transformers generate heat during operation, and adequate ventilation is essential to prevent overheating and ensure optimal performance. The required ventilation will depend on the size and type of transformer, as well as the ambient temperature of the environment. In some cases, forced air cooling may be necessary to maintain acceptable operating temperatures. Seventhly, the type of enclosure can also affect clearance requirements. Enclosed transformers, such as those installed in electrical rooms, may require additional clearances to ensure adequate ventilation and prevent overheating. Open transformers, on the other hand, may not require as much clearance, but may need to be protected from physical damage or environmental hazards. Eighthly, local codes and regulations may impose additional requirements for transformer clearances. It's important to check with the local authorities to ensure compliance with all applicable codes. Ninthly, future expansion should also be considered when determining transformer clearances. If you anticipate adding additional equipment in the future, it's wise to provide extra space to accommodate these additions. Tenthly, remember that safety is paramount. Always prioritize safety when working with electrical equipment, and consult with qualified professionals when needed. The safe and reliable operation of your electrical system depends on it. Now let's refine the specific aspects of transformer installation concerning low break elbows, wall clearances, and best practices for electrical room layout. Regarding load break elbows, also known as load break connectors, these are commonly used for connecting underground cables to transformers, particularly in pad-mounted installations. Firstly, the primary purpose of a load break elbow is to provide a safe and convenient means of disconnecting and reconnecting the cable while the circuit is energized. This allows for maintenance, testing, and troubleshooting without de-energizing the entire system. Secondly, the installation of a load break elbow requires specialized tools and training. It's essential to follow the manufacturer's instructions carefully to ensure a proper and safe installation. Thirdly, the working space around a load break elbow should be sufficient to allow for easy manipulation of the connector during installation and operation. The 18 inches clearance recommendation mentioned previously is a good starting point, but may need to be increased depending on the specific connector design and the installer's experience. Fourthly, the elbow should be properly supported and secured to prevent strain on the cable and connector. This may involve using cable supports, brackets, or other hardware to provide adequate support. Fifthly, regular inspection and maintenance of load break elbows are essential to ensure their continued safe and reliable operation. This includes checking for signs of damage, such as cracks, cuts, or corrosion, and replacing the elbow if necessary. Moving on to transformer wall clearances. As stated earlier, transformers typically do not require breathing room behind them. However, it is recommended to leave some space for maintenance and ventilation. Firstly, the specific clearance will depend on the size and type of transformer, as well as the ambient temperature of the environment. A clearance of 6 to 12 inches is a good rule of thumb, but may need to be increased in some cases. Secondly, the clearance should be sufficient to allow for easy access to the transformer's components for inspection, testing, and maintenance. This includes access to the nameplate, bushings, tap changers, and other critical components. Thirdly, the clearance should also be sufficient to allow for adequate ventilation. The transformer's cooling fans or vents should not be obstructed by the wall or other objects. Fourthly, the wall itself should be constructed of non-combustible materials to prevent the spread of fire in the event of a transformer failure. Fifthly, the wall should be structurally sound and capable of supporting the transformer's weight. Now, let's discuss best practices for electrical room layout. Firstly, the electrical room should be located in a clean, dry, and well-ventilated area. Avoid locations that are prone to flooding, dust, or excessive heat. Secondly, the electrical room should be secured to prevent unauthorized access. This may involve installing locks, alarms, or other security measures. Thirdly, the electrical room should be properly illuminated to provide adequate visibility for maintenance and repair. Install sufficient lighting fixtures to illuminate all areas of the room. Fourthly, the electrical room should be equipped with appropriate safety equipment, such as fire extinguishers, first aid kits, and personal protective equipment. Fifthly, the electrical room should be clearly labeled with appropriate warning signs and labels. This includes labeling the equipment, circuits, and hazards. Sixthly, the electrical room should be designed to accommodate future expansion. Provide adequate space for additional equipment and wiring. Seventhly, the electrical room should be designed to minimize noise levels. Use sound-absorbing materials to reduce noise transmission to adjacent areas. Eighthly, the electrical room should be designed to comply with all applicable codes and regulations. Consult the National Electrical Code and any local or state regulations. Ninthly, the electrical room should be inspected regularly to ensure that it is clean, safe, and well maintained. Tenthly, always prioritize safety when working in an electrical room. De-energize circuits before working on them and use appropriate personal protective equipment. Remember, a well-planned and properly maintained electrical room is essential for the safe and reliable operation of your electrical system. In further elaborating on electrical room layout best practices, let's address specific considerations for cable management, grounding, and equipment placement. Firstly, cable management is crucial for maintaining a neat, organized, and safe electrical room. Implement a structured cabling system that separates power cables from communication cables to minimize electromagnetic interference. Use cable trays, ladder racks, or conduits to route cables in an organized manner. Label all cables clearly to facilitate identification and troubleshooting. Secondly, grounding is essential for ensuring electrical safety and preventing equipment damage. Provide a robust grounding system that connects all metallic enclosures, equipment frames, and cable shields to a common ground point. Use appropriately sized grounding conductors and connectors to ensure low impedance ground paths. Test the grounding system regularly to verify its effectiveness. Thirdly, equipment placement should be carefully planned to optimize space utilization, accessibility, and safety. Position larger equipment items, such as transformers and switchgear, along the walls to maximize floor space. Provide adequate working space around all equipment items as dictated by code requirements and industry best practices. Group related equipment items together to simplify wiring and maintenance. Fourthly, consider the environmental conditions within the electrical room. Install temperature and humidity monitoring devices to ensure that equipment is operating within its specified limits. Provide adequate ventilation to dissipate heat generated by equipment. Protect equipment from moisture, dust, and other contaminants. Fifthly, implement a regular maintenance program to ensure that the electrical room is clean, safe, and well maintained. Inspect equipment regularly for signs of wear, damage, or overheating. Clean equipment surfaces to remove dust and dirt. Test electrical circuits to verify their proper operation. Sixthly, provide adequate lighting throughout the electrical room. Use high-efficiency lighting fixtures to minimize energy consumption. Position lighting fixtures to illuminate all areas of the room, including equipment surfaces and access pathways. Seventhly, install fire detection and suppression systems to protect the electrical room from fire hazards. Use smoke detectors to detect fires early. Install fire extinguishers or automatic fire suppression systems to extinguish fires quickly. Eighthly, provide emergency power backup to ensure that critical equipment continues to operate during power outages. Install generators or uninterruptible power supplies to provide backup power. Test the emergency power system regularly to verify its proper operation. Ninthly, train personnel on the proper operation and maintenance of electrical equipment. Provide training on electrical safety, troubleshooting, and repair procedures. Ensure that personnel are qualified and authorized to perform electrical work. Tenthly, document all electrical work performed in the electrical room. Keep records of equipment installations, maintenance activities, and repairs. Use these records to track equipment performance, identify potential problems, and improve the overall reliability of the electrical system. Remember, a well-designed and properly maintained electrical room is a critical component of any electrical system. By following these best practices, you can ensure the safe, reliable, and efficient operation of your electrical equipment. Let's further refine the guidance on transformer placement within an electrical room, considering factors such as ventilation, seismic requirements if applicable, and future accessibility. Firstly, ventilation is of paramount importance. Transformers generate heat, and insufficient ventilation can lead to overheating, reduced efficiency, and premature failure. Ensure that the transformer is positioned in a location that allows for free air circulation around the unit. Avoid placing the transformer in a corner or against a wall that would restrict airflow. Consider installing ventilation fans or louvers to enhance air circulation if necessary. Secondly, seismic requirements may apply depending on the location of the electrical room and the applicable building codes. In seismically active areas, transformers must be anchored to the floor or wall to prevent them from tipping over or sliding during an earthquake. Consult with a qualified structural engineer to determine the appropriate anchoring methods. Thirdly, future accessibility is a key consideration. Transformers require periodic maintenance, including inspection, cleaning, and testing. Ensure that the transformer is positioned in a location that allows for easy access for maintenance personnel and equipment. Provide adequate working space around the transformer, as dictated by code requirements and industry best practices. Avoid placing the transformer behind other equipment or in a location that is difficult to reach. Fourthly, consider the proximity to other equipment. Transformers can generate electromagnetic interference that can affect the performance of nearby equipment. Position the transformer away from sensitive electronic devices, such as computers and communication equipment. Use shielding or filtering techniques to minimize electromagnetic interference if necessary. Fifthly, consider the noise generated by the transformer. Transformers can produce audible noise that can be disruptive to nearby occupants. Position the transformer in a location where noise levels will be minimized. Use sound-absorbing materials to reduce noise transmission. Sixthly, consider the environmental conditions within the electrical room. Transformers should be protected from moisture, dust, and other contaminants. Install filters or screens to prevent contaminants from entering the transformer enclosure. Maintain a clean and dry environment within the electrical room. Seventhly, consider the weight of the transformer. Transformers can be very heavy, and the floor must be able to support the weight of the transformer. Consult with a qualified structural engineer to ensure that the floor is strong enough to support the transformer. Eighthly, consider the fire protection requirements. Transformers can be a fire hazard, and fire protection measures should be implemented. Install fire detectors and suppression systems in the electrical room. Use non-combustible materials for the transformer enclosure and surrounding structures. Ninthly, consider the electrical connections. Transformers must be connected to the electrical system in a safe and reliable manner. Ensure that the electrical connections are properly sized and installed. Use appropriate grounding techniques to prevent electrical shock. Tenthly, consider the overall layout of the electrical room. The transformer should be positioned in a location that complements the overall layout of the electrical room. Ensure that the transformer does not obstruct access to other equipment or create safety hazards. Remember, proper transformer placement is essential for ensuring the safe, reliable, and efficient operation of the electrical system. By following these guidelines, you can optimize the performance of the transformer and minimize potential problems. Let's now delve into more nuanced considerations regarding cable routing and management around transformers, focusing on minimizing stress on connections, ensuring proper bending radii, and employing appropriate support systems. Firstly, minimizing stress on connections is paramount to prevent premature failure and ensure reliable operation. When routing cables to the transformer, avoid sharp bends or excessive tension that could strain the connections. Use flexible conduits or cable trays to allow for movement and vibration. Support cables adequately to prevent sagging or pulling on the connections. Secondly, proper bending radii are essential to maintain the integrity of the cable insulation and prevent damage to the conductors. Consult the cable manufacturer's specifications for the minimum bending radius. Use cable bending tools to ensure that bends are made smoothly and evenly. Avoid kinking or crushing the cables during bending. Thirdly, appropriate support systems are necessary to secure cables and prevent them from moving or rubbing against other objects. Use cable clamps, straps, or ties to support cables at regular intervals. Select support materials that are compatible with the cable insulation. Avoid using sharp-edged supports that could damage the cables. Fourthly, consider the environmental conditions when routing cables. Protect cables from exposure to moisture, heat, chemicals, and ultraviolet radiation. Use weather-resistant cables or conduits in outdoor applications. Provide adequate drainage to prevent water from accumulating around the cables. Fifthly, separate power cables from communication cables to minimize electromagnetic interference. Route power cables and communication cables in separate conduits or cable trays. Use shielded cables to reduce electromagnetic interference. Sixthly, label all cables clearly to facilitate identification and troubleshooting. Use cable markers or tags to identify each cable. Include information such as the circuit number, destination, and voltage. Seventhly, provide adequate access for maintenance and inspection. Ensure that cables are accessible for inspection, testing, and repair. Avoid burying cables behind walls or equipment. Eighthly, comply with all applicable codes and regulations. Cable routing and management must comply with the National Electrical Code and other applicable codes. Consult with a qualified electrical engineer to ensure compliance. Ninthly, consider the future expansion. Cable routing and management should be designed to accommodate future expansion. Provide spare capacity in conduits and cable trays. Allow for easy addition of new cables. Tenthly, document the cable routing and management system. Maintain a record of the cable routing and management system, including drawings, specifications, and test reports. This documentation will be useful for future maintenance and troubleshooting. Remember, proper cable routing and management is essential for the safe, reliable, and efficient operation of the electrical system. By following these guidelines, you can minimize cable failures and ensure the longevity of the electrical system.